a physics-based noise formation model for extreme low-light raw denoising. Photography is all about light. Night and low light place very demanding constraints on photography due to limited foreground and escapable noise. Standard solutions of low-light imaging is to gather more light, which include enlarging aperture size, lengthening exposure time, and opening flashlight. But each method is a trade-off. A practical rescue of low-light imaging is to use burst capturing. However, it generally suffers from ghosting effect when capturing dynamic scenes in the presence of human, vehicle, etc. An imaging alternative approach is to employ a neural network that automatically learns the mapping from short exposure imaging to its long exposure counterpart. However, such a deep learning approach generally requires a large amount of paired training data that resemble real photographs in the world. Collecting rich high-quality training samples from diverse modern camera devices is tremendously labor-intensive and expensive. In contrast, synthetic data is simple, abundant, and inexpensive, but its efficiency is highly contingent upon how accurate the noise formation model is. The heteroscedastic Gaussian noise model approximates well the real noise occurring in normal lighting conditions. However, it cannot delineate the full picture of sensor noise under severely low illuminance. You can see here the objectable bending pattern artifact and unmodeled noise component exacerbated in very dim environment become clearly noticeable by human eyes. In this work, we propose a physics-based noise formation model, driving from the essential process of electronic imaging to synthesize noise dataset and show the denoising performance improvement, especially under very low light settings. Our contributions are threefold. First, we formulate a noise model to synthesize realistic noise images. Second, we present a noise parameter calibration method. Third, we collect extreme low-light denoising dataset to verify the effectiveness of our model. Our noise model drives from the inherent process of electronic imaging. The photon shot noise is modeled by a boson distribution. The read noise is characterized by a long-tailed 2K lambda distribution. Raw noise is depicted by a Gaussian distribution, and the quantization noise is denoted by a uniform distribution. Our noise model requires several parameters to be specified. We use statistical tools to estimate noise model parameters, and then model the joint parameter distributions. Please see our paper for more details. We also capture an extreme low-light denoising dataset to verify the generality of our noise model. We visualize the real and synthetic noise frames of different cameras. Compared to the Gaussian noise model, our synthetic noise frame is more realistic and close to the real noise frames. Consequently, the denoising network trained with our noise model gives rise to striking performance, which often outperform the network trained with paired real data from SID dataset. It can be seen the random noise can be suppressed by the heteroscedastic Gaussian noise model G plus P, but the resulting colors are distorted. The bending pattern artifacts become conspicuous, and the image details are barely discernible. In contrast, our model produces visually appealing results as if it had been trained with rich paired real data. Thank you very much for your attention.